the ironclad rule whispered by Albert Einstein is that nothing with mass can travel faster than the speed of light. It is the universal speed limit, approximately 300,000 kilometers per second. But what if I told you that right now, as you listen to my voice, there are objects, billions of them, that are moving away from us at speeds dramatically faster than that limit? I'm not talking about some theoretical loophole or a science fiction warp drive. I am talking about a genuine, physical, and absolutely mind-bending phenomenon that is happening in the deep dark of space. A phenomenon so colossal that it redefines what fastest even means. We're not talking about something moving through space. We are talking about space itself moving. And it is winning the cosmic race. Prepare yourself. We are about to launch into the most profound and terrifying journey of scale you can imagine. A journey that begins with a simple question. What happens when the speed limit of the universe is broken by the very fabric of reality? Come with me. We are already moving. You and I, sitting right here, are not stationary. We are hurtling through the local gravitational well of the Milky Way at hundreds of kilometers per second. Our entire galaxy is being tugged toward the Great Attractor. We are constantly in motion. But for the purposes of this journey, let's imagine we are strapped into the fastest vessel ever conceived. A craft capable of reaching 99.99% of the speed of light. It's a magnificent illusion, isn't it? To think that by moving a particle, a spaceship, or even a thought at that ultimate speed, we are conquering the cosmos. You look out the viewport, and everything is redshifted into a brilliant, terrifying blue. Time slows to a crawl for you relative to Earth, an effect described by Einstein's special relativity.
Increasing exponentially.
This is the universe's ultimate barrier. But we are going to pivot our perspective entirely. We are going to stop thinking about motion and start thinking about distance. Think of the fastest thing you know: a bullet, a fighter jet, the lightning from a summer storm. All of them are utterly meaningless in this context. The speed of light, which we will call c for simplicity, is the absolute speed limit for any information or mass traveling within the space-time continuum. This is the critical distinction. Within space versus of space. Einstein's equations, the ones that forbid us from ever hitting c, only apply to objects moving locally, objects moving from point A to point B inside the existing framework of space. But what if the points A and B themselves are being pulled apart by something else entirely? This is where our journey truly begins. We are leaving the safe harbor of special relativity and plunging into the deep waters of general relativity and cosmology. Our first stop is the discovery that changed everything. Imagine for a moment you are not in a spaceship, but inside a colossal, unbaked loaf of raisin bread dough. The raisins are the galaxies, our Milky Way, Andromeda, Triangulum, and billions more. Now, the oven is turned on. The dough begins to rise, expanding uniformly in all directions. Look around you. As the dough expands, the distance between every single raisin increases. No single raisin is at the center of the loaf. They are all simply moving apart from each other because the dough between them is stretching. This is the famous and highly effective raisin bread analogy for the expanding universe. The galaxies are not flying through the dough. They are embedded in it, and the dough, which is space-time, is expanding. This is the key to our mystery. When we observe a distant galaxy, we see that its light is redshifted, meaning its wavelength has been stretched, almost like a rubber band. This is the Doppler effect on a cosmic scale. But the redshift is not primarily due to the galaxy moving away from us. like a car on a road. It is due to the space between us and the galaxy stretching while the light travels across it. The light wave itself is being elongated by the expansion of the universe. This phenomenon was first quantified by the great American astronomer Edwin Hubble in the 1920s. Hubble's law, which we will not write as a formula, is incredibly simple in concept. The further away a galaxy is, the faster it appears to be receding from us. Think about our raisin bread again. A raisin 1 centimeter away will move away from you slowly as the dough rises. A raisin 10 centimeters away will move away 10 times faster because there is 10 times more dough expanding between you and it. Hubble gave us the Hubble constant, which we call h0, a number that tells us the rate of this expansion. This constant is currently measured to be approximately 70 kilometers per second for every megaparsec of distance. A megaparsec is a colossal unit, roughly 3.26 million light-years. So, let's unpack that number. A galaxy located at a distance of 1 megaparsec is expanding away from us at a speed of 70 kilometers per second. A galaxy at 2 megaparsecs? 140 kilometers per second. A galaxy at 10 megaparsecs? 700 kilometers per second. Do you see the pattern here? The recession velocity is directly proportional to the distance. The further out we go, the faster that distant galaxy is carried away from us by the stretching fabric of space-time. We are now ready for the moment of truth. Let's take our analogy and push it to its breaking point. We know the speed of light, c, is approximately 300,000 kilometers per second. So, what happens when the recession velocity, determined by the Hubble constant and the distance, surpasses the speed of light? We have the expansion rate, 70 kilometers per second for every megaparsec. We have the speed of light, 300,000 kilometers per second. Now, let's calculate the distance at which the speed of light is officially beaten by the expansion of space. We simply divide the speed of light by the Hubble constant. 300,000 divided by 70. The answer is approximately 4,285 megaparsecs. This distance, which we call the Hubble sphere, or the Hubble radius, is where the recession velocity of a galaxy, carried by the expanding space, becomes exactly equal to the speed of light. 4,285 megaparsecs is roughly 14 billion light-years. I know what you are thinking. That sounds like a massive, unimaginable distance. And it is. But every single galaxy beyond that 14 billion light-year boundary is currently being carried away from us at a speed greater than 300,000 kilometers per second. That is the curious, shocking reason why light is not the fastest thing in the universe. The expansion of space itself is. And this is where the real vertigo sets in. Because this superluminal, or faster-than-light, expansion is not just theoretical. It has profound existential consequences for us. Think about a galaxy just 1% further out than the Hubble sphere, say at 14.1 billion light-years. That galaxy is receding from us at 101% of the speed of light. If that galaxy decided to send us a signal right now, a powerful laser beam, a photon traveling at the absolute local speed limit of 300,000 kilometers per second, would it ever reach us? The answer is a resounding, terrifying no. The light is moving toward us at c, but the space underneath it is expanding away from us at a speed greater than c. It's like trying to walk toward the back of a train that is moving forward faster than you can walk. You are moving, but your position relative to the starting point is actually moving backward. The light is permanently caught in a cosmic treadmill, moving forward but constantly losing ground. It will never, ever reach us. and the situation is getting worse. In the late 1990s, two independent teams of astronomers made an astonishing Nobel Prize-winning discovery. They were using Type 1a supernovae, exploding stars that act as standard candles for measuring cosmic distances, to precisely map the expansion rate of the universe. The teams, led by scientists like Saul Perlmutter, Brian Schmidt, and Adam Rees, expected to find that the expansion was slowing down due to the pull of gravity from all the matter in the universe. Instead, they found the exact opposite. The expansion of the universe is not slowing down, it is accelerating. This acceleration is driven by the most mysterious, dominant force in the entire cosmos: dark energy. Dark energy is a bizarre form of energy, a kind of anti-gravity that is intrinsic to the vacuum of space itself. As space expands, more space is created, and with it, more dark energy, which then drives more expansion. It is a self-reinforcing runaway process. This accelerating expansion has created something even more dramatic than the Hubble sphere. It has created the cosmic event horizon. The cosmic event horizon is the ultimate frontier. It is the boundary beyond which light emitted now will never, even in the infinite future, be able to reach us. Think of it like the event horizon of a black hole, but in reverse. A black hole's event horizon is a boundary of no return for anything that falls in. The cosmic event horizon is a boundary of no return for any light trying to get to us. Right now, the observable universe, everything we can currently see, is vastly larger than the Hubble sphere. We are still receiving light from galaxies whose space is expanding superluminally. How is that possible? Because the light we are seeing today left those galaxies billions of years ago, when the universe was younger and the expansion rate was slower. Back then, the light was moving fast enough to cross the distance before the expansion rate truly accelerated. But as the universe ages and the acceleration continues, those superluminally receding galaxies are moving further and further out of our reach. They are crossing the cosmic event horizon. And once a galaxy crosses that horizon, it is gone forever. Its light will be stretched by the expansion until its wavelength is so long that it is effectively invisible to any technology we could ever conceive of. Imagine the last photon from a brilliant, magnificent galaxy. A photon that has been traveling for billions of years, finally crossing the line. It is a silent, tragic farewell. And every second, more galaxies are crossing that threshold. The superluminal expansion driven by dark energy is effectively shrinking our cosmic neighborhood. As more and more of the universe recedes faster than light, the night sky of the future will become a desolate, empty canvas. In 10 trillion years, any future civilization in the Milky Way will look up and see nothing but the handful of gravitationally bound galaxies in our own local group. They will have no idea about the Big Bang, no idea about the other billions of galaxies, no idea about the vast, rich, and strange cosmos we can see today. All the evidence of the universe's history will be red-shifted out of existence, carried away by an expansion that is not only faster than light, but is also accelerating. So we return, now, symbolically, to our starting point. We are back on Earth. The fastest thing we can move is still a photon, 300,000 kilometers per second. But we carry with us a profound, humbling realization. The speed of light is the local speed limit for motion. It is a law of physics, but the expansion of the universe is a global phenomenon for space itself. It is a property of the cosmos, and that property has no speed limit. It is the reigning champion of the cosmic race, a silent, invisible force that is not only pulling the universe apart, but is also erasing all evidence of its own existence
We are
from the future
accelerating
sky.
past the projected threshold.
What does that make us?
Gravity fluctuations
What does it
increasing
mean for our place in
exponentially.
the cosmos, knowing that we are living during the only time in the universe's history when we can actually see the whole story? Are we simply witnesses to a vast, accelerating disappearance? And what other cosmic laws are we misunderstanding right now, simply because we haven't looked far enough?